Well, the proposed agenda is to go through inverse functions today, but I'd be shocked if anyone else shows up. So I guess based on last time, do you want to follow up with anything you've been studying so far?
Um, I think what we did last week was good.
Was good? Yeah. Okay. So nothing else from there was particularly challenging, or anything else has come up that you want to have a look at?
Not as of yet.
Sure. Okay. So I guess the main thing, if we're going to do this agenda here for inverse functions, would be usually around how you do the like quadratic or other non-one-to-one function inverses. So mainly that'll be the main focus, at least as far as the more challenging questions there. How are you when it comes to inverses as a whole?
It's not bad.
Not
It's
bad.
okay.
Sure. I mean, do you want to just jump straight into doing the questions then, or shall I do a quick overview?
We can start with questions.
Easy. Okay, let's give them a shot. So first up, we'll just do a quick test of understanding here. If we jump straight to, geez, they're doing only linear. Trivial. Anyway, so we can jump straight to 2e here. So basically all we're doing is finding inverse and then state domain and range of that inverse. So you can either just do that whole thing yourself and then tell me the answer, or you can even just talk about it, whatever you'd rather do.
I got y equals negative half x plus 6.
Y equals negative half x plus 8 is what it says in the answer. Let me just double check, that makes sense. Yeah, half of 16, 8. Unless you were doing a different one. Yeah, just double check the working on that, I guess.
Yeah, sorry, 8.
Yeah, okay, cool. So that's the inverse function itself. Then the next part of that is also domain and range.
For the range, I got the domain that they gave there.
Yep.
And then for the domain, I got R.
Domain of all real. Not quite R. So the fact that you know the range is -1 to 7, if you imagine plotting the inverse that you got for all real numbers, that's not going to have a range of -1 to 7 anymore. And so if you know that you've got to cap it up at the top and bottom of 7 and -1 respectively, there's going to be a certain set of x values that give you that. That's going to be your domain. At least that's one way of thinking it. The other way, you could even just go back to the original function and figure out its range, and then just flip the two. Both is acceptable. Usually you do the second version, where you go back to the original function and then give it and get its range, because when you do the inverse, sometimes you get a really nasty thing, and it can be kind of tough to figure out what the range is of that thing, or what the working backwards to get the domain can be a bit trickier than just starting with the original.
If we use the way you said by going back to the original, would you put the domain that they gave?
Yeah. So you would know that a linear is already an increasing graph, or at least, hang on, let me double check. Is it increasing or decreasing? It is decreasing, right? Negative linear. So you already know that the upper and lower bound of your domain are going to be the upper and lower of the range, just because you can picture the linear in your mind. Whereas if it's a quadratic, then suddenly you've got to worry about turning points. So really, you just got to drawing a quick sketch of the thing is usually a good start over whatever the domain is, and then you can see, yep, biggest y values here, smallest y values here.
Uh, so it's decreasing, so would it be negative infinity to 7?
Uh, well, it's still -1 to 7 as domain goes, but what I was saying by decreasing is just that you know that if I sub in -1 as the x value, I'm going to get the biggest y value. And if I sub in x equals 7, I'm going to get the smallest y value. So if I quickly sort of show that on the handwriting, if we got 16 minus 2x, so we're looking at a y-intercept of 16, and minus 2x means it's gone downwards. It's going to finish somewhere over here at 7. It's going to go up a bit further and cut off at -1 there. And so that gives you an idea of at least what the graph is going to be like. And so when you look at this, you can say for certain, this is my biggest y value, and this is my smallest y value. Therefore, if I find those two things, I'll find the range. Cool?
Yeah.
Yeah. So obviously that's just a matter of set x equals -1 and set x equals 7. That gets you your two y values for the range. And then obviously to finish that up, once you have range and domain of original, you just flip those to get domain range of inverse. My graph isn't to scale, by the way. I just noticed that it should all be positive over this domain, since the x-intercept would have been 8.
Would the highest y be 18?
Yeah, highest y would be 18. Yeah. That would give you the upper bound of the domain once you flip it to inverses. Just need that lower bound now.
Would it be 0?
Not 0. I tried to redraw my graph to make it a bit easier to see what's going on. We want to stop at x equals 7. That's the end of our domain, which is going to be a little bit above. So you're just going to sub in your y equals 7.
So just be 2.
Oh, sorry, it's the x equals 7, not y equals 7. And yes, it'd be 2. Yeah, that's all. Sub in values, get the y values, and then flip them around. So final answer, you got domain of 2, 18, and the range is -1, 7. Any questions there?
No.
Okay. So we'll do another one just so we can get the hang of that again. We'll do another one that's quite similar. So part B also has a pretty specific domain on it. So try that one.
Wait, sorry, which one?
2B.
Okay.
This one has an interesting result. Once you find it, I'm curious to hear your thoughts as to why it is the way it is.
The inverse I got y equals -x plus 3.
Yep, -x plus 3 is correct.
And then the domain I got was 1 to 5.
Domain of original or domain of inverse?
The domain of the inverse.
Should be range of the inverse, that one, because 1 to 5 is what you started with.
Oh
So,
yeah.
yeah,
Sorry, yeah. The range is 1 to 5.
yep, that's
And
good.
then the domain I got 2 to -2.
That's it, yeah, 2 to -2, correct. Now the question I have is a more conceptual one. Why is it the inverse is the same as the original? How did that happen? It is correct, but how could that possibly happen? the hint would be to think about what does it mean if you try to take the inverse of something or find the inverse of something.
Um,
Another. Oh, go ahead.
if we plot it on the same like graph, it would be the same like graph.
Yeah, no, correct. If you put it on the same axes, you'll get the same thing. But why did
Yeah,
it come out to be the same?
I'm not sure.
Not sure. That's fine. So here's another hint on the handwritten bit. Oh, whoops. This dotted line here, the line y equals x. What is that? Why is that relevant in the context of inverses?
It's because that's the line that it mirrors on.
Yeah, it's mirrors, correct. And so right here is going to be the graph of 3 minus x. Or at least trying to. It's perpendicular. And so if it's already symmetrical before flipping, then trying to flip again across the line y equals x, nothing's going to happen. All right. So since y equals x has a gradient of +1, and this has a gradient of, what's that, negative, hang on, yeah, -1, they intersect at a right angle. And so for that reason, you've, yeah, it can't flip and change. It flips into itself. Cool?
Yep.
Sweet. Okay. Because that could be like a one marker, like, hey, why is the inverse? They like to do these little like theoretical one marker questions. But okay, so that's basically the theory behind all the question two. It's all linear, different domains, different ranges. Ready to move on to a bit more complicated?
Yep.
Sweet. Okay, so question three, what you'll notice is that there's all these quadratics and square roots, and that's because it's a bit more challenging to figure out what the inverse would have to be, specifically around getting the domain and range of the inverse. Rearranging for like to get the actual inverse function itself usually isn't so bad. It's more so trying to get the domain and range afterwards that becomes a bit of an issue. Do you want to give one of them a shot immediately, or do you want to work through one?
Could we work through one?
Certainly. So let's have a look. The challenge that we run into with these types of functions is that they're, well, at least in the case of the quadratic, it's not a one-to-one function. And if you try to do this flip along the line y equals x with a function that is not one-to-one, you get a relation, not a function. In fact, do I have a picture of it? Yeah, you'll end up with this, basically, which not a function. And so one of the things you have to do is ensure that your function is one-to-one. So in this exam scenario, we've got a quadratic and it's being defined over a specific domain. It's got all negative numbers to the left-hand side, and then it cuts off at a specific b value. So usually one of the very first things you have to do is figure out, how do I make my function one-to-one? Because the only way I can find an inverse is to make it one-to-one. Any thoughts on how you might make a quadratic one-to-one?
Would you set a domain for it so it wouldn't be a function anymore? I mean, a relation anymore?
Yeah, so you want to make basically set the domain to force it to be one-to-one. Yeah. Now, you'll notice in the actual question, it'll either cut the upper bound up or cut the lower bound off. The question now becomes, conceptually speaking, I don't need to know the exact number, what would or how would you go about finding that cutoff point?
Would you see like the direction the graph is going and then do it based on that?
Yeah, that's a good idea. So we got this quadratic here. Based on what you're looking at, how much you cut it off.
Half of it.
Half of it. As in, like, split it down the middle?
Yeah.
Yeah, okay. So yeah, basically you're going to set that upper bound as the -2 because that's where the turning point is. Because if you cut it off at the turning point, you'll notice that whether you go left or right, it'll be 1 to 1. Now we are forced to go left because we're told it has to go to -infinity, and so that upper bound must therefore be the turning point. Worth pointing out, that's only if you want to maximize all the possible domain out of it. You could cut it off here and then go all the way left. That'll still be 1 to 1. It just means this is the very last point at which you could cut it off. Cool?
Yep.
Awesome. So as far as finding that turning point, you've got a billion ways of doing it. You could complete the square, you could do calculus, you could do -b over 2a, you could find your two x-intercepts and do the midpoint. Take whatever method you want out of that. Do you want to explore any of those, or are you happy enough with how you get that?
Yeah.
Yes, happy enough, or
Yeah, happy enough.
okay. Yeah, okay. And so now that we've actually achieved that, we've set up our domain properly, we can now effectively find the inverse. And so what you do is you obviously start with your function. Now, starting with this, pretty difficult. Because if you swap your x and y here, you're going to have a y and a y squared to work with. Pretty tough to just get y on its own. So the best thing you can do is try to rewrite your function in a way where there's only one y to work with. And in the case of quadratics, there's a guaranteed way of forcing that to happen, and that is with the completed square form. So pretty much always you want it in completed square form, because then when you do your swap, you'll notice there's only one thing to keep track of. And so yeah, I've gone ahead and rewritten the notation ahead of time to make it f inverse, but you can just start by swapping x and y and then rewrite it at the end. That's totally fine. And then yeah, nothing too crazy from here. So you subtract 9 to both sides, you do the multiply by -1, you square root both sides, and you subtract 2 from both sides. Tricky part, we get a plus minus that's associated with the root. Do you remember how we handle that?
Is it we look at the domain and if it's negative, we go for the negative one? Like if it's negative infinity too.
Yeah, okay. Look at the domain. I have to think about that. If it's pointing left, then you pick the negative. Yes. Yeah, that is correct. Yeah, if it's pointing left, you pick negative. If it's pointing right, you pick positive. Yeah, that always does work out. That's just not the way I think about it personally, but that works. Yeah, I'd have to think about that for a bit. And so yeah, I've got a slightly different way of doing it, but if you then look and see final answer, there you go. You pick the negative instead of the positive. So if that's the way you like doing it, then do that, and don't worry about what's in the book. Yeah, that's all. So let's apply that. So do you want to try part B yourself, or do you want to work through that together live?
Could we do it together?
Yeah, certainly. So let me write that down. So we have y equals x minus 2 all squared plus 3. And we're doing it over the domain 2 to infinity. Those are our parameters. All right, so first up, we'll try and find the inverse. How are we going to find the inverse?
Swapping the x and the y.
Yep, swapping x and y, that's good. X equals y minus 2 all squared plus 3. And then as far as getting the y back, what are we doing?
X minus 3.
Yep, x minus 3. What else?
And then we square root both sides.
Yep. It's y minus 2. Yep,
And then just add the 2.
that's it. y equals 2 plus minus square root x minus 3. Technically, we say f inverse, so we can put that in now. Cool. All right. What do we need to do to fix it up?
We just used the plus one, so 2 plus square root of x minus 3.
That's it. Yeah, just the plus. Because, yeah, domain was pointing to the right, so we used the plus version. And I guess just for fun, what we just did was find, so we had x minus 2 plus 3, which means there. We had this one, and we just found that, more or less. Cool. Okay, that's that. That's pretty much as complicated as that's gonna get for quadratics. Square roots actually end up being easier. In fact, I wonder if when we do a square root, if that method of figuring out, well, no, because when it's square root, you don't even have to care because it just is that. There's only one possible answer. There's no plus minus. So yeah, square root should be fine. I wonder if 4a will be challenging. Let's find out. So if we have y equals square root 16 minus x squared, and we're going to do that from 0 to 4. First things first, what are we going to do?
Swap the y and x.
Yep. And then rearranging. So how's that going to work?
Can we square both sides?
Yep. X squared equals 16 minus y squared.
And then move the y squared, so it'd be y squared minus, and then move the x back to negative x squared plus 16.
Yep. That's good.
And then we can square root.
Square root. Nice. 16 minus x squared. Now I am curious. This is a domain that's pointing right. Do we still take the plus on that? I wonder if that also works for this scenario. Because that's a circle. Oh, sorry, a semicircle, I guess. But that's only the positive root. That would be, if I remember correctly, that'll be this from negative 4 to 4, but we only want to have a part of that. So that would be this initially. 0 to 4. Kind of feels like we should just get the same thing. Because if you flip that in that line, it's symmetrical either side already. So it is, right? Yeah. So yeah, seems like even in that case, you still take the plus because it's pointing right.
Yep.
Nice. That's good. It's good that it works in a lot of different scenarios. Or at least 2 that we've tested. Cool. Alright, that's that. And then I guess the only thing that will be left that would be remotely difficult might be question 8, which would be solving for unknowns based on inverses. So let's have a look. So first up, we've got y equals square root a minus x, and it's for negative infinity to a. Oops, that a should have been a square bracket. First question is find f inverse, so that's sort of whatever. Do you want me to just blitz through that, or you want to explain through it?
You can do it.
Yeah, okay. So we flip x equals root a minus y. x squared equals a minus y equals a minus x squared. Okay, so f inverse a minus x squared. Cool. Now the next part is the graphs of f and the inverse intersect at x equals 1. From that, what must the possible values of a be? So basically, f equals f inverse at x equals 1. That's what that piece of information was telling us. What do you think we might do to solve for possible values of a?
Would we sub in x equals 1?
Yeah, we can sub in x equals 1. Where?
Into the inverse?
Okay. F inverse x, or I guess f inverse 1 equals a minus 1 squared. So f inverse of 1 must therefore be a minus 1. Okay. What else?
Would we make the original function and this equal each other?
Yeah, exactly right. So you grab the original function. So that's going to be the square root a minus x. Not forgetting, of course, that we still have our x equals 1 conditional. So basically a minus 1 equals square root a minus 1 in this case. And then, yeah, that gives you one equation with one unknown in it, and so we can solve for that. There is a pretty quick answer to this that you might be able to see off the bat, just by kind of looking at it. Any thoughts on where these would be equal? You don't have to know it off the bat. We can solve for it, of course, but curious to see if you can see a quick and easy number that would work. The a equals 1 in this case. If that goes to 0 and that goes to 0, then they're both 0. So that will be one possible solution there. And you can only see that because they're so similar between each other. You got an a minus 1 here, you got an a minus 1 here. It's like, okay, cool. If this one goes to 0, then this one will go to 0. But otherwise, yeah, we can just do our rearranging. So how would you rearrange and solve this?
Would you square both sides?
Yeah, sounds like a good idea to me. A minus 1 all squared equals a minus 1. What else?
And then get the a on the other side?
Which a? There's a couple. What, bring this over here? Right to left?
Yeah.
Yep. A minus 1 all squared minus a equals minus 1.
Would we expand the a minus 1 squared?
Yep, I'd like to do that. So you're going to have a squared minus 2a plus 1 minus a equals minus 1. So that minus a came from here. That was just the expansion there. All right. What do we do from here?
And then it would be a squared minus 3a.
Squared minus 3a.
We can take the 1 to the other side. So it'd be -2.
Yep.
And
Looking good.
then we could factorize the a squared.
We can, yeah. We might run into a bit of an issue, but yeah.
Oh, we could like, instead of doing that, we can move the 2 back there and make it equal 0.
Yeah, that's better.
That'd be better.
Yeah. So to do any factorizing stuff, you need null factor law. So I'm sure you quickly figured that one out. Cool. Okay. What do we do with this?
We could go a minus 2, a minus 1 equals 0.
Yep. A
So
minus
a
2.
equal 2 and 1.
Yep. That's it. A equals 1. A equals 2. Yeah, that'll be mathematically correct there. Let me just double check and see if there's any restrictions on A. A just has to be a constant. That's it. So yeah, that's sorted. Nothing else really there. So I guess, yeah, in summary, what we had started with was some generic root function. We were given a specific domain associated with it. Although, actually, there is a domain. Let's make sure that we haven't picked a value that breaks this. Would both of those a values have worked? So if we consider either a equals 2 or a equals 1, are these both going to work out with their respective domains? Well, we can find out pretty quickly on the CAS. Much easier than just sketching all that out a bunch of times on the hand. I don't think it should be an issue, but it's worth at least exploring a bit. So we can have our square root of a minus x. That's the first function. Then we've got the second function, which is, trying to think if I bother putting a domain on it now. Nah, maybe later. The other one is going to be a minus x squared. Yeah, probably should put a domain on it. So that one we already know is defined from basically all x less than equal to a. X less than equal to a. And then this one would be, okay, so if that's from all x less than equal to a, it's a positive root, so that means we're going to have think about that one. So for this one, range would be square root pointing that way. So we're now looking at a as a lower bound. So all x greater than a. X greater than equal to a. Okay. And then, yeah, let's just test a few values. So a equals 2, firstly. H of x. I of x. Nice. Just gonna double check I plugged them in right. A minus x squared. A minus x. Yeah. Okay. And if I define A equals 1, okay, well that's interesting. So only A equals 1 actually works. That's the only way they actually intersect at x equals 1. So yeah, definitely was worth the exploration then, it would seem, because if we didn't, we would have got it slightly wrong. So that would have been a matter of, obviously if you had to do that by hand, you'd have to sketch each of those individually over their domains. But yeah, fair enough on what was going on there.
Yeah.
Cool. Okay, so you would obviously then just cross that one off. Only A equals 1. Yeah. So that was a sneaky little thing, because it wasn't like there was any indication in the question itself that would cause, well, it didn't say like A had to be like a natural number or a specific domain on it. What it did have was A was part of a domain, and that was the cause for alarm. But otherwise, yeah, that'll be about as tricky as that gets, at least as far as the book stuff goes. I have definitely seen some really strange exam questions that'll have like a full tilt square root with all sorts of stuff on the inside. And a lot of the time, what they'll do is they'll say, figure out the value for A for which the intersections have some number of solutions. Like if I won't spend too much time trying to find it. So what I'll do instead is just sort of draw it from memory. Like let's say you have a function like this and its inverse like like this, right? And in this particular circumstance, I know it's not really to scale at all, so you know what, I'll just fix that. Let's make it actually an inverse pair. This and like this. Cool. So this kind of scenario would have two intersections. But one of the kinds of questions that comes up is there becomes this like parameter h where, or k or whatever, which can basically cause these graphs to shift either up or down with respect to each other. And so if you shift it up far enough, you get it to a point where they are tangent to each other, kind of like that, in which case you have one solution for choosing a specific value of k, or you can shift them apart even further, in which case you have no solutions because they never are able to cross that barrier. So that's the hardest questions that come up, and usually a lot of it is just playing with CAS. Like there's no algebra you're doing there. The functions are way too complicated for it, and so you just gotta sort of play with it that way. Have you seen anything like that?
No.
Not particularly. Okay. I mean, we've got time, so let me see if I can pull one up. I'll see if because I had to do work solutions for one of them, I recall. Now I just got to remember what past exam it was, so bear with me for a bit. I don't think there's anything else that we'll go through other than this, unless there's anything you want me to dive into.
No, that's all good.
Sweet. Okay. Should be able to find it pretty quickly just by looking at the pictures. Or at least relatively quickly. Surely it's not in one that I haven't finished yet. That would suck. Because I only make PDFs of the work solutions I've fully done the exam for. Hopefully it's not in one of those. No, not that one. Oh, Kind of. Yeah, this is another common thing that comes up with inverses as well, which is because they are very often the case where they will like have a bound area between them because they do intersect across. It'll often ask you to figure out a certain value that would force them to have a bound area. And in this case, you're looking to not only just have a bound area but minimize it. And so, if we look at yeah, maybe we need a bit more context of the question. So we've got f, which is the cubic. We've got the secant between it. Area equation. F inverse, tangent. Inverse. Oh yeah, there we go. So there's the green line is your inverse, and the red line was the linear that we were given at the very start. And so because you already had the full equation of the original function, you can get the full equation of the inverse. That's nothing crazy there. But what is different is, sorry, I misspoke. This red line, this is new. You have to figure out taking a tangent line such that this area in here gets minimized. So you want to figure out where can I draw this tangent on my graph to ensure that the area bound between the two things is minimized. And so one possibility is like this. All right, if you took the tangent line there, you would have all of this as bound area. Following so far?
Yeah.
Okay. And so the goal is like, where do I put this value such that all of this shaded red is minimized? And so this is one of those where it uses the previous answer. Bugger. What you do is you use the fact that the inverse is sort of symmetrical about the line y equals x, and you take that the answer from what we had previously. So this is tangent with respect to the original function. What we had was tangent with respect to the inverse function. And the thing that you have to draw the relation between is the fact that because those are reflected symmetrically, this area for this set of tangent line is the same thing as the area of the other set. And so in the previous stuff, we already figure out all those coordinates that you need to achieve that. And so all you do is you just use the values and flip the x and y to get there. There's probably a lot more context I need to give to fully appreciate what's going on in this one. It is a how many part up until, oh geez, it goes even further. G. So if you're at all interested in seeing like the extent to which they start asking these types of inverse things, what I'll do is I'll drop the 2019 exam solutions in here, or at least my take on the solutions. And yeah, have a read through question 5 if you're at all interested in that. Cool?
Yep.
Sweet. I mean, otherwise, yeah, I don't really have anything else to specifically go over. So unless you want me to clarify anything, we can end early. Up to you.
I think it's all good.
All good? All right, I'll let you go. Enjoy
Yep.
the
Thank you
6
so
or so
much.
minutes back in your day.
Okay, see ya.
Take care.